introduce and welcome Yulij Ilyashenko for his lectures this morning after the Coxeter lectures of last week. It's another lecture of superexact asymptotic series and monodromy maps of polycycles. So Yulij, when you want.
Thank you very much, Jean-Philippe. Do you hear me?
Very well, very well.
Wonderful. So it's my pleasure to continue my lectures here in Toronto. Greetings to everybody. This is a continuation of my Coxeter lectures. Let me. The plan is the following. The first part is a very brief recalling of what I have said in my first Coxeter lecture in order to connect superexact asymptotic series with differential equations and polycycles. The second part will be a definition of superexact asymptotic series of class n of their exponents, coefficients, and index. And the third part will be ideas of the proof. The state of the matter is the following. For n equal 1, I delivered the matter in my last Coxeter lecture. For n equal 2, everything that I will speak about is now proved. For higher n, there are some details not yet completed, but many things may be said about n equal to and arbitrary n in a uniform way. So I will speak about arbitrary n and point out what things are to be done. So I recall that the monodromy map of a polycycle is an analog of the Poincaré map. This map is a composition of the so-called correspondence maps or Yulij maps from one cross-section to another near a singular point inside its hyperbolic sector along the orbits. The desingularization theorem guarantees that these singular points may be considered as hyperbolic saddles and saddle nodes only. So let us speak about hyperbolic saddles. The correspondence maps of hyperbolic saddles may be decomposed in the asymptotic Yulij series. The formula for the Yulij series is written here, and it is a simplest sample of the superexact asymptotic series to follow. The feature is that the coefficients of this series are not numbers, but more complicated objects themselves. So the term of a Yulij series is this one. Exponential has an exponent Uj zeta, and the polynomial in zeta is a coefficient. Yulij series do approximate the extensions of the correspondence map to so-called standard quadratic domains. The images of the right half plane with the disk deleted under this map. And this is a definition of almost regular mappings. So once again, correspondence mappings for hyperbolic saddles belong to a class of almost regular mappings. And what is important, these mappings are written in so-called logarithmic coordinates. That is, zeta is equal to negative logarithm of z, and z is a natural parameter on the cross section. And almost regular mappings are holomorphic in some standard quadratic domain, are real on the real positive semi-axis, and can be expanded in an asymptotic real Yulij exponential series. Expandability means that for any nu greater than 0, there exists a partial sum approximating the mapping to within exponent of negative mu psi. Nu is arbitrary large positive number. So for an arbitrary large number, we can find a corresponding partial sum. And the theorem says what I already have said, that the Yulij mapping of a hyperbolic saddle written in a logarithmic chart extends to an almost regular mapping in some quadratic domain. Now, a more complicated thing is a correspondence map of a saddle node. A saddle node has a stable manifold and a central manifold in the real domain. In the complex domain, the stable manifold is holomorphic, and the central manifold is usually not. So the Yulij map for the real saddle node to the central manifold has the form, I write it from the right to the left, a normalizing cochain, then delta standard, then G, a holomorphic germ. A normalizing cochain normalizes the monodromy map of the saddle node. This monodromy map is a parabolic germ, and I described the theory of parabolic germs in my first lecture. I will not go back to it. Delta standard is given by an explicit formula, and I want to stress that for k, it is exponential of -1, you may say over z, but instead of z, you have a more complicated elementary function. Yet for k equal 1, a equals 0, this elementary function is exactly z. So this is z generalized, if you wish. And G is a holomorphic germ at a fixed point 0 with a positive derivative, but not necessarily real. The maps like this form the class 2, and there is a class from of inverse maps. The first part of the talk ends up by the structural theorem. The monodromy map of a polycycle of an analytic vector field is a composition of the maps to, from, for real saddle nodes, and of almost regular germs from R. R is the set of almost regular maps that are real on the real axis. So this is all about the differential equations. Now we want to characterize these compositions geometrically. We illustrate the composition by a function or a graph of a function, a broken line. A segment of a broken line that corresponds to an almost regular map is horizontal. The segment that corresponds to the class 2 makes one step down. And for the class from, the segment makes one step up. The composition is balanced if the characteristic of the composition has the same values, 0, at the end of the domain where it is defined. It is easy to see that a non-balanced composition is either flat, like the exponential map, exponential -1 over z at 0, or inversely flat. Definitely, such maps cannot have fixed points near 0. Non-balanced polycycles can have no limit cycles that accumulate. So we study only maps with a balanced composition. This is a graph of a characteristic of a composition. And what is important? The horizontal segments show the maps that occur on the level. This is level 0, this is level 1. The most deep level is level n. And the higher the level is, the more complicated are the maps that will occur in this level. Structural theorem makes us to think in an opposite way, because maps from very restricted classes are present in this composition. But we are not satisfied by a characteristic like this, where the pits are intermingled with maps on the high level. We want to collect all the pits together, the most deep first, then less deep, and so on, then the maps of level 0. And for this sake, we have to make the maps on level 1 more complicated than on level 0, the maps on level 2 more complicated than the maps on level 1, and so on. Therefore, the definitions are inductive in N, and in particular, when we define superexact asymptotic series for the maps that occur on the level N, then we should use all the previous constructions related to the compositions of a smaller depth. So now, after these preliminary notes, I pass to the definition of star n. The star n are the series like this, with the exponents ej and coefficients aj. The set of exponents is en, the set of coefficients is kn. Now, in order to define en, we will use superexact asymptotic series of level n-1. This is inductive in n. Base of induction is n equals 0, and asymptotic series of level 0 are deluxe series. Now we will use somewhat extended group of all compositions of depth n-1 from the structural theorem. In what follows, we will need a conjugacy with the exponential map. It is simply denoted by A. A applied to F is this composition. In the previous lectures, I have shown that a position like this may produce from F having the form identity plus decreasing exponential, this composition produces from F a map identity plus doubly decreasing exponential. And this conjugacies, repeated several times, produces maps of the form identity plus towers of decreasing exponentials. We will need some semigroups that belong to the group Gn-1. It appears that the elements of this group do not oscillate. This is our main goal to prove for the group corresponding to the depth n, and by induction we suppose that it is already known for the group of the depth n-1. And for this group, it appears that the following number from R plus infinity is well defined. This is, I skipped the limit here, the limit at infinity of the ratio a to the negative n applied to G and divided to psi. Those G for which this limit is 0 form a slow subsemigroup of Gn-1 with minus. This means that G has a slowly decreasing discrepancy, difference with identity, and such that the limit is the group with the subscript rapid has a rapid discrepancy, so that this limit is a real number. And the semigroup with superscript plus is a semigroup with this limit equal to infinity. We will use mainly this subgroup, Gn-1 minus small. Now I can define the set of exponents of the class n. Any element of this set is a partial sum of a superexact asymptotic series of the previous class whose terms do not tend to 0. Imaginary parts of these terms do tend to 0, not only for the exponents, but for all the terms. Any element is from En has a principal exponent. The limit of exponent divided by the iterated exponent, the exponent that iterated n times. And the most tricky requirement is that if we compose the exponent with the logarithm n iterated n times, then the real part will be smaller than mu psi for some mu. Psi is real part of zeta, and the modulus will be smaller than mu times modulus zeta. This holds in a standard domain of class n. I will not define these standard domains. I will only say that first, they are similar to quadratic standard domain. That is, they are more narrow than standard domain, than a half plane, but more wide than any sector located in the half plane. And when n grows, the domains become more and more narrow. So that's it about the exponents of the class M. Now, the coefficients of the class M, similar to the coefficients of the class 1, have rank R and are defined by induction in R. The notation is KNR for the set of coefficients of class N and rank R. I did not say that I am a little bit cheating. The actual definitions are a little bit more complicated, and for any N, there are two kinds of cochains and series, but I will neglect this difference for simplicity, and I hope that it will only clarify the situation. So the set of coefficients of rank 0 are the map cochains of class n-1 composed with exponential taken n-1 times, apply iterated n-1 times. Square brackets show the iteration power, and they are missed here. And iterated with any element of the group Gn-2. The induction step is produced in the following way. We suppose that the set of coefficients of rank R is already defined. For the base, R is 0. Then we define series of the rank R. And this is very simple. These are series with the exponents from En, which does not depend on the rank, and with the coefficients from this set already defined. And we define cochains of class N and rank R. These are cochains for which the composition with the exponential iterated n times may be decomposed in superexact asymptotic series for this class. The decomposability requires special definition, but I skip it. When we have cochains of rank R, then we can construct coefficients of rank R plus 1. The construction is the following. Coefficients of rank R plus 1 are old coefficients plus the set of the following compositions. F of iterated exponential of G. And what is new here is F. It is taken from the class defined right before the definition of this K. F is from this new class of cochains, and G is from the slow semigroup that I have described. So this is the inductive definition of the coefficients of rank R. And when we take the union of the coefficients of all the ranks, we get the coefficients of class N. Now we define an index of level N. An index is attributed to coefficients, to series, to cochains, and index defined for the objects of class N is also, in fact, an index of level N. So, strictly speaking, we should denote it by index sub N. But we agree that all the indexes that we consider today are of level N, and we write simply ind for simplicity. So index of a coefficient is a set of elements of Gn-1 minus slope. index of a coefficient from the zero class of zero rank is empty. Index of a cochain from the corresponding class, which constitutes this set of coefficients, which is used in the definition of this set of coefficients. This index is empty too. Now, let us pass to the index of the coefficients of this. When we know the index of the coefficients, we define index of series just as a union of indexes of coefficients. A series has an infinite number of coefficients, so this is an infinite union. But the requirement is that this infinite union should be nevertheless a finite set. So this is index of a series. Index of a cochain is an index of a series that approximates f iterated with tower of exponents. We index is not univalent, but we fix the series and attribute this index to the cochain. So index of a cochain is now well defined. And index of this composition is index of the cochain combined, composed with G plus G itself. I recall that the index is the set of elements from the group G8-1. And as I said already, the index of a series is the union of the indexes of the coefficients. The requirement is that this union is finite. So this is the end of the rather cumbersome definitions, and we pass to the study of these series. The goal is having a partial sum of star n to distinguish a leading term. But the difficulty is that the coefficients and the exponentials of exponents have similar nature. And when you have a product of a coefficient to an exponential, you may take an equal term with another exponential and another coefficient. Some factor is moved from the coefficient to the exponential or vice versa. So it is not so easy to distinguish a leading term. And instead of that, we write a representation like this. These are exponents, h1, here is exponent of h2, and so on. And here is exponent hi plus 1. Here is a, which is from a set of compositions with the level n minus 1, and the remainder terms are with numbers, with substrings, are all smaller than the corresponding exponentials. So this R1 is smaller than the exponential mentioned here, and so on. So first of all, the exponentials themselves do decrease in a sense. And this exponential is an element of the set of all exponentials composed with gk minus 1, the element of the index. And these elements do decrease in a sense that every gk decreases at infinity faster than gk minus 1. So we compare these elements of the groups at infinity, and every subsequent element decreases faster than the previous. So we take these exponents, and either this exponent is identically 0, or it increases. The typical exponent from En is just exponent to the power n, exponential function iterated n times. So the exponential, the exponents from the exponents with number k increase faster in the modulus than the denominator. Tower of n exponents composed with gt. So, in a sense, these exponentials are, oh, I have lost exponential here. Sorry, I've read this formula many times, but all of them is exponential h2 and exponential hi plus 1. So A is in the 0 rank coefficients, and the remainder terms decrease in such a way, I do not give detailed comments, they decrease in such a way that they do not influence the asymptotics of the full expression. Now, a lower estimate theorem for the cochains of class n is exactly the same as for the cochains of class 1. They are greater than some decreasing exponential. For any f, its own kappa exists, such that this is equality. So this is the main result of the theory of the superexact asymptotic theory of star. If you remember the additive decomposition theorem, this estimate allows us to deduce finiteness theorem from the additive decomposition theorem. So this is a principal conclusion. It is elementary for the cochains that are approximated by the Yulij series, non-trivial Yulij series. And this is the consequence of the theory of star n for an arbitrary n. So the previous theorem makes use of the following principal term here. Any non-zero, non-contractible partial sum of a star n has this form. What does it mean non-contractible? This means that it is not equal to a sum with a smaller number of terms. In particular, this will guarantee that S is not So this factor is in a sense a leading one. S is dominated in general by this factor if H1 is not equal to 0, and R1 is negligible in comparison with S. So this is one version of the principal terms theorem, and this is another expression. Just once again, here I will have exponential of H2, and the following requirements, this is the continuation of the same statement, the following requirements are given. H1, H2, R1, R2 satisfy the requirements of the principal representation theorem. Moreover, the exponents of S belong to En composed with G1. If n equals to 1, this is the same as to say the exponents cannot grow, say, faster than exponent of zeta divided by 2, whilst the exponents from E1 may grow like a simple exponent. X. So, in the first case, the exponents of S belong to this class. In the second case, they belong to this class. And in both cases, the number of elements in the index of S is slightly smaller than that for the partial sum. And this will allow us to write down a similar decomposition for S and to use the induction of the number of in the number of components of the index. These J's are called components of the index, and this G1, these G's, and this G1 is the maximal component because they are. This was the statement of the theorem for the case when the index of the partial sum was non-empty, and it was G1 and so on. And if it is empty, then the following representation holds, and H, A, and R satisfy the same requirements as H I plus 1, A, R I plus 1 in the principal representation. Now we come into the following reduction lemma. Suppose that first of all, a definition. Consider a partial sum of the series n minus 1, and consider G from this semigroup. We say that partial sum is 0 modulo this exponential, provided that it grows no faster than this composition. The limit at infinity is a number from R, and this limit may be 0, but cannot be infinite. If the sum is not equivalent 0 modulo this composition, then it grows faster than this composition just by definition. And what is important, that if this sum is negative, then it tends to negative if the imaginary part tends to 0. And the reduction lemma is the following. Let us take an exponent from En, an element from this semigroup, and suppose that this exponent grows no faster than this composition, or in other words, is 0 modulo this composition. Then this exponent belongs to the set of exponents of class n combined with composed with G. The proof of this lemma for n equal 1 is very simple, and I will show it now. I recall you the definition of the exponents of class 1. It repeats, in fact, the definition of exponents of class n, but the asymptotic series from that definition are, in this case, the Yulij series, and therefore the definition is much more explicit. Exponents of class 1 are partial sums of the Yulij series, like that, like this. The sum is finite, Pj are real polynomials, and mu's here are from 0, 1. If mu j is 1, then Pj is constant. That is, there is no term growing faster than exponential zeta in this sum. The principal exponent is defined as this, and it exists by definition. So what is most important is this formula. Now we suppose that this sum grows no faster than exponential combined with multiplication by mu. So we suppose that this ratio tends to some constant, probably 0. Then the exponential is this constant times exponential of mu zeta plus the sum of quasi-polynomials. A quasi-polynomial is product of exponential to a polynomial. And these quasi-polynomials have an exponent smaller than mu. Then, if you combine this exponent with mu inverse, then you get simply constant to exponential plus sum of the quasi-polynomials with exponents smaller than 1. And this is exact what is allowed for the exponentials from E. So this proof of the reduction lemma for n equal 1 is very simple. This innocent proof is not at all similar to what happens in the case n greater than. For n equal to 2, the reduction lemma is now proved, and the proof takes more than 20 pages. For n greater than 2, the proof is expected to follow the same lines, but is not yet complete. So now I am in the middle of the ideas of the proofs. I stated several theorems that will apply the lower estimate theorem. And let us go back. Let's begin with the last theorem, principal term theorem, case of non-empty index. In the case of empty index, the arguments are similar, but I will not present them. So the trick is the following. We want to find this decomposition. For this, we want to find h. We take the index, and g is the index of the sum, and g is the maximal exponent of this sum. let us call an exponent, another exponent of this sum tame if it is a comparable, once again a typo, it is E0 instead of H. E minus E0 if this difference is comparable with 0 modulo this composition, then the exponent here is tame. So E0 is standing here. And it is wild if the equivalence does not take place. If E0, at this moment, H did not appear, it appears right now. If E0 is tame, let H be identically 0. If E0 is wild, let H be equal to E0. So in the first case, H is identically 0. In the second case, H is E0. Now we take the sum of all tame terms and divide it by xh. And this ratio is S. We take the sum of all wild terms divided by xh, and this is R. From the definition of tame and wild, it follows that R decreases as fast as the principal terms theorem requires. Конечно, у меня сейчас доклад. So we get this decomposition. And now what is required from S? It is required that the exponents of S belong to En of G, not S itself, but exponents of S. But this follows from the reduction lemma, because the exponents of S are comparable with 0 modulo this composition. So this is an important exponents of S are of this kind, and this is the first requirement for S. Once again, because of the definition of wild terms, R is estimated from above by this decreasing exponential, by this decreasing combination, for any u greater than 1. Now we did not discuss the index of S yet. And the requirement is that the number of components of this index is smaller than that for the original partials. So to discuss the index of S, we introduce special and non-special partial sum. A partial sum of star n with all the exponents in En of G is called special if G is the maximal component of the index of this partial sum. And non-special, I should not say in the opposite case, but I should say it is non-special if G is greater than all the components of the index of this partial sum. This is a typo. So not all partial sums of star n are either special or not special. So I gave almost a complete sketch of the proof, but I said nothing about the index of S. So S is a sum whose index belongs to index of sigma n. If S is non-special, then G does not belong to index of S. Then index of S is contained in a smaller set in comparison with index of sigma n, and we are done. If S is special, some extra techniques is required, but not too long. I will not say more about this part. Now, how the principal representation theorem is proved. It is deduced from the principal terms theorem by induction of the cardinality of the index. And in my last Coxeter lecture, I have shown how this induction works in case n equal 1. In case of arbitrary n, the induction works in the very same way. So this is the way to prove the sketch of the proof of the principal representation. The lower estimate theorem is deduced from the principal representation theorem, once again, as in case n equal 1. So there is no serious difference between the case n equal 1 and greater than 1 at this point. And when we prove the lower estimate theorem, then we are done. I should confess that I even did not mention many other technical steps that are needed. But my goal was to give you an idea of the superexact asymptotic series and of their relation to the finiteness theorem. And this is what I wanted. Thank you.
Thank you very much. Thank you very much, Yulij.